Everybody, I'll just start. Hi, my name is Sankey Lee. I'm at the AOML PhD. Oops. Yeah, today I'm going to talk about the fragile relationship between El Nino and California rainfall. Here are the people who contribute to this work, and this is outline of my talk. So probably you have seen this picture or maybe a different version of this picture. So what it shows is that during the winter and spring of the El Nino events, usually this atmosphere stream usually comes southward, and then it strengthens toward North America. So therefore, that increased the storm activity, winter storm activity over this line. So it increased the rainfall over the California and the northern Mexico and all over the southern U.S. So there are a lot of papers documenting this very well-known relationship. And of course, during the La Nina, almost opposite happens. So what I'm showing you here is the rainfall over the California and the nearby neighboring state during these three El Nino events, 1982, 83, 1997 and 98, and 2015 and 16. So these two events are known as the strongest events that we ever measured in the 20th century. So the California experienced a third wettest winter and spring in 1982 and 83 here, and the wettest winter and spring in 1997, 1998, since the record started in 1895. So this, what I'm showing you here, is the spatial temporal evolution of the SST anomaly in the tropical Pacific, average between 5 degrees south to 5 degrees north. So this is the longitude along the equatorial Pacific, and this is the time. So this is January, from the January of the onset year and to the December of the decay year. So this is the spatial temporal evolution of the SST anomaly during these three events. So what happened was that around the beginning of the winter in 2015, the Nino 3.4, that is SST anomaly in the central tropical Pacific, was extremely strong at that time. So at that time, so people thought that that could definitely end the most severe multi-year drought ever recorded in the state of California. So that was really a big drought condition, and historically as well as in the geological timescale, it was a very extensive drought there. However, as many of you know, the California experienced just a near normal rainfall during the 2015 and 16 El Nino. And then, did I say that the 2015, I forgot. Did I say the 2015-16 El Nino was the strongest El Nino event of 21st century? Probably I skipped that part, sorry. Yeah, and then so that's why people expected that. So you can see that the rainfall increased slightly over the northern basin, northern California, but nothing much in the central and the southern part. So the basic question that I like to address today is that why some El Nino events have a large or little impact on the California rainfall. So that's kind of broad question that I have. So of course, so let's just go back to this question about why this 2015 and 16 El Nino failed to influence the California rainfall. There could be many different reasons, but one important reason could be potentially the cause is the internal atmospheric variability, what is known as the Pacific North American pattern, shortly PNA pattern. So for instance, this is, I'm getting from the Weather Channel. So this is typically the jet moves way down, and then it brings the storm path to the south and go this way. So it increased the rainfall along the California. So, and then during the positive phase of PNA, you have opposite. So this PNA pattern could disrupt or enhance the teleconnection that is coming from the tropical Pacific. So that's one potential cause. And then another reason could be the El Nino intensity. So for instance, the study by Ho et al. Hoyle et al. Was a recent study. It's a purely statistical research showing that the El Nino intensity has to be more than 1 degree Celsius. The Nino 3.4 should be more than 1 degree Celsius to be able to influence the California rainfall. And this moderate strength and weak El Nino don't really have an effect. However, this hypothesis doesn't apply for 2015 and 16 because that was pretty strong here anyway. So next one is a special pattern of the El Nino SSD, El Nino or SSD, and that's kind of a direction I'm heading my presentation. So this is the from the Joe et al. In this study, what we did was that we look at the SSD patterns and the associated convection pattern in the tropical Pacific before the regime shift in 1998 and 1999 and after that. So when we look at it, there is a strong differences between these special patterns. One, before the regime shift, the anomaly was centered over the central and eastern Pacific, and after the regime shift, it actually shifted to the west. So there's no convection anomaly here. This, by the way, this is outgoing long wave radiation, which means that this is more rain, this is less rain. And then also this recent study by Beck et al. Suggested that the 2015 and 16 is sort of like this, so a Central Pacific El Nino compared to the other two big El Nino. So what I'm showing you, so I'm comparing the atmospheric dynamics associated with these three El Nino events, and this you showed it, you saw it in the earlier slide. This is the rainfall anomalies, three El Nino event, 82, 83, 97, 98, and this is the geopotential height anomaly, geopotential height and wind anomaly at 500 millibar in the middle of the troposphere, associated with these three events. And what I'm showing you here is the rainfall anomaly. You can think of this as the heating rate in the troposphere, how much it heats the atmosphere due to the latent heat release. So during these two earlier events, you see that the atmospheric jet stream has shifted. You can see that this is coming straight toward the North America. And if you look at it more carefully, it's a kind of small picture, but United States is here. And then you can see that it kind of penetrated across the US West Coast here. So that brings more storm into the Western US. And then you can see that you see the same thing during this time, 97, 98, it completely penetrated the west coast of the United States. But in here in 2015 and 16, this anticyclones, or we call it Aleutian low patterns, Aleutian low, which is pretty strong in the wintertime. That, of course, this is anomaly, did not get into the United States, to the North America. So it was there. It was teleconnection pattern was there, but it was kind of separated from the North America. So it really didn't have much impact on North America. So this is basically what it is. Pretty simple. And then if you look at the convection anomaly in the tropical Pacific, you see that the there is a increased convection activity in the far eastern Pacific here, but nothing here. So so this is kind of consistent with earlier paper by Joe et al. Like that. So all right, so I'm going to show in the later slide that the convection anomaly here is really key to creating this teleconnection pattern. All right, so let's take a closer look at the three El Nino events more closely, SSD evolution patterns. So this is the 82, 83, 97, 98, 2015, and 16 cases. So I put this line here from January to May. The reason is because if you do the correlation between the El Nino index and California rainfall, it is maximum between January to May. And of course, El Nino is the strongest in November and December. The correlation is just almost zero. So there's no point in looking at the El Nino evolution during this time. So it's important to remember that it's a January to May. That's California rainfall. So you see that there's two patterns. Of course, they are different, but they share one similarity. That is, during this winter and spring of the decay years, this Far Eastern Pacific acid anomaly was pretty robust. It persisted in this case, beyond April, beyond May to the summer. And you can see the same thing here. But in this case, 15 and 16 cases, you see that it was very strong, just like the 1970-98. But during this time, it dissipated pretty quickly. So by March and April and May, April and May, this Far Eastern Pacific SS anomaly just dissipated. It's gone. So that is, I think, it's the main reason. So consistent with this SSD pattern during the January to the May. Oh, by the way, I think I forgot to tell you that what I'm showing you here is the average between January to May. This whole thing is anomaly during this season. Sorry. So you can see that the consistent with this SSD patterns during the January to May, there was a robust convection activity over here, but not really during this time, during this El Nino events. Okay. All right. So the main hypothesis here is that based on the analysis of the three El Nino events, main hypothesis is that warm SS anomaly in the Far Eastern Equatorial Pacific should persist throughout boreal spring and winter and spring to significantly enhance rainfall across the state of California, and that is due because of the teleconnection pattern and position of the Aleutian low, etc. that I talked to you about. So I have two specific questions that I'd like to address today. First question is, how do the Far Eastern Equatorial Pacific warm SST affect the relationship between the El Nino and California? Basically, I'd like to understand the atmospheric mechanism, the exact mechanism of this. So we use a simple two-level atmospheric model to address this question. Question two, so we look at just the three El Nino events, right? But El Nino events since 1950 to now, we had 25 of them, and they're all different. So we need to actually look at different types of El Nino. And in an earlier study in 2014, we identified 4 most frequently recurring patterns of the El Nino flavors. And then, so we're going to look at the rainfall in the California associated with these 4 patterns, 4 flavors, and the associated atmospheric dynamics. So next slide, we're going to address question 2 first. So here, so those are the 4 patterns that we identified there. So I'm going to spend next 2 minutes to explain a little more about this. So probably you have heard about canonical El Nino, Modoki El Nino, Central Pacific warming pattern, Eastern Pacific warming patterns, and then warm pool El Nino, cold El Nino, so many different types of El Ninos. Probably you have seen it. But all your studies, what they do is that they actually focus on the special patterns during the peak season, that is the DJF, December, January, February. So they do perform EOF and all that. But thing is that El Nino, DJF is not the only time that is important. During the springtime, we know that thunderstorms, hails, and tornado in the United States is very important in the springtime. And also summertime, we know that it is very important for the hurricane. Irma is here. So I know that that's a big thing. It's difficult to really focus on my research, my presentation, because last night I was looking at the track. It is coming right to us, and who cares about El Nino? Anyway, yeah. So anyway, so El Nino in summer is very important because it suppresses the hurricanes in the Atlantic Basin. Also, it increases activity in the Pacific. And also, summertime teleconnection is very important for the southern hemisphere. That's where there's a winter. It's a winter there, right? summer for us is a winter there. So teleconnection in the southern hemisphere is all about boreal winter. So other seasons are very important. So what we did was that instead of just looking at DJF SST, we make this plot. So 5 degrees south to 5 degrees north, we average that along the equatorial Pacific. So as a function, so it is all the El Nino events are expressed in terms of longitude and also time. So 2 months period, onset to decay period. So I have 25 of them. So I performed the inter-El Nino EOF analysis. So x-axis is longitude, y-axis is the month, and the PC, principal component, is not in terms of time because the time we have already used. The principal component is in terms of El Nino number 1, number 2, number 3, all the way to 25. So it is a little kind of a unique EOF analysis. So that's how we get this 4 different patterns. So first of all, transitioning El Nino. This is basically characterized by the rapid transition of the warm to cold SST in the far eastern Pacific. We have many different examples of those El Nino events. And then we have the resurgent El Nino that is relatively weak El Nino event that persistent long enough to create another one in the next year. And 2014 and 15, that just happened 2-3 years ago. That's basically a good example of 2014, good example of resurgent El Nino. And then many of the people don't actually treat this as the El Nino, but if you go to CPC, they actually now identify that as El Nino, weak El Nino. And then we have a persistent El Nino, of course, 82, 83, 97, 98. That's exactly the persistent El Nino. And if you remember the SS evolution during this 2 period, it looks very much the same thing. Maybe we can go back. Yeah, this 2. That's basically a persistent El Nino type. Of course, we had these 2 cases. We had another one in 1957 and 8, which was a pretty weak one though. And we had an early terminating El Nino. This El Nino is a kind of weak El Nino that favors the early development, premature kind of development of the cold SS anomaly in the far eastern Pacific. And many of the time, this doesn't really lead into La Nina. This is lead to La Nina, but this just dissipates most of the case. So we have 4 different types of layers.
Previous page, I don't understand why 2014, 2015 is resurgent.
Oh yeah, that is one year before.
Right. Okay.
Yeah, 1 year before, which I'm not showing.
Gotcha.
But yeah, so that was an El Nino, and then have another one. So
Gotcha.
yeah.
When you say the 4 most frequently recurring, is there like a 5th and a 6th type? And they cover 80%, 60%, 90%?
Yeah, so this 2 mode explains little more than 60% of the inter-El Nino variance. So this actually represents first 2 EOF modes. So different types of different negative phase and all that. So there is a PC3. The PC1 is explained 35 variance, and then PC2 is 27. PC3 is slightly below 10. So that is very interesting because I was talking about that 3rd term with my collaborators. Yeah, it is there. 10% is there. Yeah, we look at 3rd, and then we found that there are many things that actually fall into that category, but we haven't really done anything on that. Yeah. All right. So yeah, but this is a little more. So this is a PC1, PC2. So this area is persistent, early terminating, transitioning, resurgent, and then there are some mixed types there. For instance, this is 97, 98, 82, 83, 57, 58. They all fall into the persistent. And then what is interesting is this 2015 and 16, and that was it's a mixed type. but it's a one of its kind, which means we never had this kind of thing before. This is a very unique thing that happens. And then, of course, a mixed type is very rare, but this one, the transitioning and early terminating mixed type, there seems to be a lot of them. So probably you should pay attention to this one too. Anyway, and then, of course, there are two events that we cannot really characterize by any of the combination of this four category. Okay, so that's a little too much. So yeah, let's take a look at how the atmospheric patterns and California rainfalls are associated with these four different flavors. First, transitioning El Nino. You can see that the rainfall is increased mainly over the northern California. You see, if you see dot, that's statistically significant at 95 significant level. And then you see that along the coastline, there are some increases here, but not for the entire state. So you can see that this is the convection patterns. You see this pattern, this part is kind of missing. Convection here is missing. And also this anticyclone is barely touching the United States, barely touching it, but I can see that, due to the atmospheric variability, sometimes it can affect this region. So it's not that big, but it can happen during this time. And then for this resurgence El Nino, this whole thing, the anomalous cyclone is a state far away from the United States, so it doesn't really seem to have much impact on it. So transitioning El Nino, yes, kind of. Resurgent El Nino, no. Let's take a look at the persistent El Nino. Of course, by the way, this is all regression study. You see that the rainfall is increased for the entire state of California, all significant, and you see this precipitation anomaly in the far eastern Pacific, and you can see that the cyclone anomaly kind of penetrating across the coast, U.S. coast, West Coast, and then affecting this California region. And for the early terminating El Nino, nothing much. And then there is a very weak anticyclone there, cyclone there, but it is, again, far away from the North America. So persistent, yes, definitely. Early terminating, not really. Very little impact. So that addressed the question 2. We will go back to that questions. So now let's take a look at more about the atmospheric mechanism here. So here we like to understand why the far eastern Pacific convection anomaly, SST and the convection anomaly is important for the California rainfall. For that, we use this model, simple model we developed here in 2009. And this is the simple two-level stationary Rossby wave model. And this model basically combines Gill's atmospheric, the baroclinic tropical atmospheric model, combine that with the barotropic stationary Rossby wave model that is very popular among the atmospheric scientists. So I thought that in 2009, what I saw was that there are tropical people were always working with the Gill model to explain what happened in tropics and all that. And then there is a kind of a teleconnection people who are interested in extratropical region that always use the stationary wave model. This is basically, the stationary model is basically barotropic vorticity equation model. And then what they do is that they prescribe what we call it Rossby wave source. Rossby wave source is basically a advection of the vorticity, anomalous vorticity by the mean flow, and also it's a linear combination of it. So it's a very complicated kind of source term. You have to calculate it from. It's not very intuitive. You have to get it from reanalysis. You have to calculate it actually, and then you prescribe it. Then you can see the nice teleconnection patterns. All right, but I thought that there is something is missing between between these two communities. So I thought that you should combine it. So we developed this model. So here, what you only have to do is that you prescribe SST or the convection in the tropic, and it will calculate the gill circulation tropic as well as the teleconnection to the extratropic. So here is an example of what I did. So here I prescribed the realistic background flow for the northern winter and northern summer, and I just prescribed the idealized heating anomaly over here, and this is the teleconnection patterns associated with it. So it clearly shows that the teleconnection is favored only in the winter hemisphere. So for instance, June, July, August, it doesn't really create anything, which is how the nature works. So what I did was that I just played with the 1982-83 El Nino events. So I prescribed the convection anomaly derived from the rainfall anomaly, and then I just I convert the unit and then force the simple model. So I'm going to show you 3 slides. So this is the convection anomaly that I put it in the model, and this is the model response. So this is the stream function and the rotational wind, barotropic stream function and the rotational wind components. And you can kind of compare that with the geopotential height and wind at 500 millibar. So you can see that there is this the atmospheric jet stream shifts southward, and this anomaly, this cyclone anomaly, penetrating across the west coast of the United States. So it's reasonably realistic. So it is captured at teleconnection patterns. So what I did was that, okay, I used the same forcing, but I just forget about all these things. Let's just focus on the diabatic cooling, anomalous cooling in the Western Pacific, and force the model and see what happened. Then I see this nice teleconnection patterns here, but this cyclone here, it is kind of a stay within the North America, and also it affects the kind of north of the California, for instance, Oregon and Washington and British Columbia. Of course, I mean, this model is not really designed to pinpoint exactly what state it would affect it or all that, but it actually shows some general characteristic that it's going to move southward, move northward, and a little bit to the west compared to the all forcing here. And then what if we just forcing it? This is the same thing, same as the previous slide, the whole total forcing. What if we have only the forcing only in the Central Pacific? Then in that case, this looks very interesting because you see this anticyclone is occurring, but much to the south. So it is centered along the U.S. coast, around 20 degrees north, and you can see that the wind should be the westerly wind should be decreased north of it, and westerly wind, or the trade wind here, not trade, it's still westerly in the upper troposphere, is also increasing over here. So this so the California is over here, right here. So this the wind will be increased, and the storm activity will decrease. So we may have a decreased rainfall here. So this definitely doesn't explain what happened in 1982 and 83. So the last one. So let's just forcing the model with just the Eastern Pacific SST of the convection anomaly and see what happened. Then of course the strength is much weaker than the total, but if you look at the phase of it, you see this anticyclone and cyclone anomaly, and you can see that this cyclone here over the North Pacific and another one in the over the United States, over the North America, they seems to be merged together, and then it become as one, and definitely that will be much more effective in terms of bringing the storm path further to the south into the California there. So this simple experiment show that this Western Pacific cooling not going to help, Central Pacific not going to help, this is what you need to get the California rainfall increase during the El Nino. So this explained the atmospheric dynamics associated with it. That's it. So it was like 30 minutes. So here is a summary. So the question one was that what is the mechanism related to the effect of the Far Eastern SST anomaly onto the California rainfall? So I will just read it. So according to the simple model experiment, if the Far Eastern Equatorial Pacific is not warming up throughout this whole winter and spring to produce the persistent convection anomaly above, then the anomalous cyclone in the North Pacific will be positions away from the United States, U.S. West Coast. Therefore, the relationship between El Nino and California rainfall will break down. So the Far Eastern SST is very important. And this mechanism is definitely applicable to 2015 and 16 El Nino. Number two, so what about the different types of El Nino or different flavors? How do they affect the California rainfall? So this is a summary of it. So basically, it has to be persistent El Nino, which means the Far Eastern Pacific warm SST has to persist throughout the spring. Then it will have a significant increase in rainfall in the entire state of the California. And of course, during the transition El Nino, occasionally it will increase the rainfall, but not the entire state, but the northern and coastal regions. And for the resurgent El Nino, early terming El Nino, they are not really strong enough in the Far Eastern Pacific to actually create a strong teleconnection into the California. So that's it. And then I have some additional questions. So one question. So do the current state-of-art climate model reproduce the observed inter-El Nino variations related to the Pacific, which means does the model can actually simulate the persistent El Nino well? And then there was a recent study by Yoon et al. They showed that the majority of the climate model that participated, the CMIP-5, that is a coupled model intercomparison project phase 5 model, they failed to capture the persistent versus early terming El Nino. So second year of both, they failed to capture, majority of that failed to capture in a sense that the maximum SST occurs in a different region, different time. So they doesn't look like what we see in the observation. So that was the case. And then also what it means is that they didn't talk about it, but what it means is that all this seasonal forecast model, climate model that we are using currently, they're basically CMIP-5 model. They are GFT models, ANCHOR model, NSEM model, and so on and so forth. So that means that a seasonal climate model may suffer the same model deficiency. So they may have some difficulty in predicting the persistent El Nino. So that could be something to further investigate. And there are additional questions that I'd like to really think about it later. One is that, yeah, I don't have a slide for this, but so it's difficult to explain. But this 2014 and 15, we had an El Nino, very weak one, but we had another one. So the one question is, we had an El Nino in the 2014 and 15 that actually warms up the atmosphere globally, everywhere. Then another El Nino come along, then the atmosphere will be much stable because it's warm. So that it will be difficult to have more convection with the same amplitude of SST. So that could be a suppressant. So it's a preconditioning effect may suppress the El Nino in 2015 and 16. So that's one thing that I'd like to explore. And the last question is, how about the global warming? Yeah, I don't think I have that. I had a, but the global warming. If you look at the trend of the SST in the tropical regions, Western tropical Pacific and Indian Ocean warms much faster than the Central Pacific. So that this global warming actually create a very unique spatial pattern. So it this pattern actually stabilized the Central Pacific regions in the atmosphere. So that could have some impact on the. So there are a couple of papers by, for instance, Kuma et al. And Lim et al. 2010 and 2015. They already talked about this. So this is some very important, interesting topic to explore. All right, thank you very much. Any questions?
Yeah. I didn't really understand your 4 EOF modes. You're saying that they are from 2 PC modes that
Yeah.
are opposite trends in the same mode?
Yeah.
Okay.
Yeah.
So that's because you mix space and time, right?
Yeah, it's a little
mirror each other, right?
it's a little complicated. What happened is that for the UF analysis, what we do is that we take out the mean of the El Nino. So mean of the El Nino is there. So later when I show it, the mean is actually went into that. Mean El Nino plus anomaly.
Okay, yeah.
So we're talking about anomaly of the anomaly. So that complicates everything. That's why I don't show it like that. So.
And so overall, so this total is only 60%, right?
Yeah, the whole thing. Yeah, this explains PC2 to about a little more than 60% of variance. Yeah.
Okay. Question about this characterize to the next slides. So there's only 2 PC1, PC2. You didn't show how to put this all the events into 4 characters. So how do you do that?
Yeah, this is the thing. So for instance, if the PC1 is positive, then it's transitioning. If the PC mode is negative, then it's a resurgence.
Yeah, but and also the persistent.
Same thing. So it's if it is PC2 is positive, then it's a persistent. If PC2 is negative, then it's only terminating. They supposed to, it is the EOF analysis, they should have a mirror image, right? If a spatial temporal should mirror image. But the thing is that there is a mean effect, El Nino, composite mean, that it was added there. That's why you see it's a little complicated. Yeah.
So like the 52 event looked like the average El Nino, so it
Yeah.
didn't reflect on any of those.
Yeah. That's true. Yeah.
Another question. So in your model simulation, you basically consider how the location of the enhanced convection affected the California rainfall. So but the point one here you made is if the ENSO is not persistent into the next year's January to March, you usually cannot cause enhanced rainfall in California.
Yeah.
So is it possible? I mean, the atmosphere mean state also affected the stationary Rossby wave train. So if the jet's location will modify the reflecting of the wave train.
Yeah.
So is that possible?
Yeah, that is definitely possible. So one idea is to perform this this simple experiment. Here, by the way, the mean state is average between 1950 to 2016, whole year. But if we ever separate the mean state into different time, maybe before 97 and after 97, then this the mean structure will slightly change. So that will definitely affect the teleconnection. And isn't that what your question?
So yes, so here the right panel is average for that winter or okay.
Oh, this one?
Yes.
Oh, this is just a model result. This is anomaly. Anomalous stream function at 500 in the barotropic stream function. So this is the averaged convection anomaly during the January to March. So model is a really steady state thing. It doesn't really have any time evolution, so it just gave me this. So this is the kind of time mean. And then that question, earlier question, we kind of addressed that question in the earlier paper in Joe et al. So what we did was that we changed the mean atmosphere circulation background before 1970 and after 90. We mixed it everything and then experiment that doesn't seem to have a much impact. That we talked about it in that paper in 2015. Thanks. You look unhappy. You. Any questions?
Santi, I see
Yeah.
this as an excellent example
Yeah.
of research
Yeah.
in applied oceanography in support of NOAA mission.
Yeah.
Linking the ocean to weather events. From the work that you have done and you are doing, where do you see this going to be able to provide out the contribution of El Nino in outlooks for California or West Coast rainfall?
Yeah. Yeah, I think what I like to do is I like to take a look at the seasonal forecast model and how well they represent this 2-year mode. And then I'm thinking about that direction. So thinking about creating the index for the persistency, and then the transition. So to PC1, PC2, maybe those two can be a good index for the indicator of the rainfall over California. So yeah, but we need to really take a look to see if the seasonal forecast model can actually capture that pretty well. So that's
Okay, good. Thank you.
Yeah. You can ask me later. You know where I am. So all right. Thank you very much.